In this last section, we'll look at the link between chemical equilibrium and what we learned in the last chapter over chemical kinetics and rate laws. If we imagine we have the reaction A plus B in equilibrium with its products C plus D. This is a reversible reaction where A and B can form and combine to get C and D, or C and D can combine and form A and B. So if we imagine the forward reaction, we could describe the rate as R sub forward. Or if we imagine C and D combining to make A and B, we could call that the rate of the reverse reaction, or R sub reverse. If we want to write the individual rate laws for our forward and our reverse reaction, we could say that the rate of the forward reaction is equal to the rate law constant, K, and we'll call it K sub F for forward reaction, times the concentration of our species A and B. We could also write the rate law for the reverse reaction. R, the rate for the reverse, will equal the rate law constant K sub R times the concentration of C times D. At equilibrium, the rate of the reverse reaction is the same as the rate as the forward reaction. That's what chemical equilibrium is. So we could set these two equal together at equilibrium. So we could say K sub F times the concentration of A times the concentration of B is equal to K sub R times the concentration of C times the concentration of D. And if we move our concentrations over to the same side and move our rate laws over to the same side, so let's take K sub R and divide both sides of the equation by that. It would cancel here. And then let's divide both sides of the equation with the concentration of A times B. Moving that over to the right side, so that would cancel from here. What we would be left with is K sub F divided by K sub R is equal to C times D in the numerator over A times B in the denominator. And that fraction is equal to our equilibrium expression. We have the ratio of our products over our reactants raised to the coefficients from the balanced equation. So that whole thing is actually just equal to K sub C. So what this does is it gives us another way to calculate the equilibrium constant if we know the rate constants of the forward reaction and the reverse reaction. So we could say that K sub C is equal to the rate constant of the forward reaction over the rate constant of the reverse reaction. If the forward reaction is favored, then the value of K sub F will be a large value. This means that we're going to form more of our products, C and D in this case, and we'll have a product-favored equilibrium with a large value for the equilibrium constant. So K sub C will be a big number. If the opposite is true, then the rate of the reverse reaction could be favored. In this case, we're going to have more of our reactants at equilibrium, so the concentrations of A and B will be greater. A reactant-favored equilibrium will end up having a small value for K sub C. So if K forward is bigger than K reversed, then that means we have a product-favored equilibrium with a large value for the equilibrium constant. If K forward is equal to K reversed, then our products will be equal to our reactants. K sub C will be in the range of 10 to the negative third to 10 to the positive third, which is considered to be about 1. That's when our reaction is close in terms of the rate of the forward or the reverse, and so we have about an equal amount of products and reactants. If our reverse reaction is faster than our forward reaction, then our reaction will favor the reactants being formed, and we'll have a small value for the equilibrium constant. Consider the following reaction. At 76 degrees Celsius, the forward and reverse rate constants are K sub F equals 0.13, 1 over molarity times seconds, and K reverse equals 6.2 times 10 to the minus fourth, 1 over seconds. What is the value of the equilibrium constant K sub C? Is the reaction reactant or product favored? So we derived that K sub C could be calculated by taking the rate constant of the forward reaction divided by the rate constant of the reverse reaction. Our K sub F is 0.13, 1 over molarity times seconds. So the forward reaction, just looking at the units, must be second order. And our reverse reaction has a constant 6.2 times 10 to the negative fourth, 1 over seconds. And so K sub R, the reverse reaction, must be first order. Just looking at the units on the rate law constant. Now K sub C is a unitless quantity, so we really don't have to worry about these units. When we divide K sub F by K sub R, we get 210, and so that's our equilibrium constant. Now, is the reaction reactant favored or is it product favored? In this case, K sub F, the rate constant of the forward reaction, is greater than K sub R, the rate constant of the reverse reaction. So this would mean that the reaction is going to be product favored.